Uh, in the lectures that we have seen so far, we have looked at a number of examples where we took some modeling instances and showed how we can create the description using Verilog. Now, in this lecture we shall be starting our discussion on the various ways in which we can model or create the description of a system or a digital block that we are trying to design. So, the topic of our lecture is Verilog description styles. Okay. So, broadly speaking, there are two different styles of description. I have already given you some examples of these. So, you have seen some examples, but broadly speaking the description styles can be categorized into two different types. Okay. The first one is the so called data flow description style, which uses continuous assignments using the assign statement that you have already seen in many examples. So, this uses such kind of assignment statements using assign. Now, as an alternative, you can have behavioral design or description styles as well, where you use some kind of procedural statements which are somewhat similar to a program in a high level language that you sometimes write. You see, whenever you write a program in a high level language like C or any such language, you try to specify what exactly you are trying to do, the different steps. Okay. So, this is what you or this is how you specify what you are trying to do. So, in that sense the behavioral model is somewhat similar. So, you use some kind of procedural statements which is similar to the construct which are available in a high level language, these we will see. And here in place of continuous assignment, we shall be using a different kind of assignment statement called procedural assignment, which again is of two different types. One is called blocking assignment, other is called non-blocking assignment. So, over the next few lectures we shall be discussing these different alternatives and variations and see that which one to use, when and why. Okay? Fine. So, let us start with continuous assignment or the data flow style, which I have already seen in sufficient detail, but just for the sake of completeness let us also look at it once more. So, the data flow design style is identified by the keyword assign. So, whenever you want to make some assignment like a equal to b plus c or sign equal to z 15, bit number 15 of a vector z, we use this keyword assign before that. Now, I mentioned earlier also, whenever we use an assign, this forms a static binding. It is not that whenever this statement is executed, b plus c is computed and the value is stored in A, not like that. Whenever you write A equal to b plus c, something like this will be happening. Let us say b is a register, c is another register. So, there will be an adder which will be generated, which will be adding b and c, and the result will be generated or stored in a net which you are calling A. This A is not a register, it is just a net. So, whenever either B or C will change, this A will change immediately after the delay of this adder. Okay. So, there is no concept of any clock or anything. Such an assignment we said earlier also is referred to as continuous assignment, right. Okay. So, there are some constraints in such assignment statements using assign. First thing is that the left hand side must be a net type variable, typically a wire. But however, the expression that we are using on the right hand side here b plus c, here z 15, these expressions may consist of variables which can be either net or register or any combination of the two. And this is called continuous assignment because this is continuously active. There is no signal that tells you that when this operation will be carried out and when the output will be stored in that target. So, it is not like that. It is some kind of continuous assignment. Whenever one of the input changes, the output net value will be changing or be affected right away after the necessary delay of the circuit. Okay? Fine. So, these kind of assigned statements, typically we use it for modeling combinational circuits, but we shall see that we can also use this for modeling sequential circuit elements, which are of course not very common, but we can also do this. We shall be taking some examples later, right. Okay. Now, in a Verilog module, we can have any number of assigned statements, and this is a very typical structure. So, whenever we write a Verilog module, let us say this is a Verilog module, it starts with the keyword module, it ends with end module. So, in the beginning, we typically start with the signal declarations. All the net and the register type variables are declared there. Then after that, we usually club all the assigned statements together. This is the normal practice, and then the other kind of statements will come, which you shall see later, right. This is how a typical Verilog module structure look like, where the assigned statements are typically placed in the beginning right after the signal declarations. And another thing I also mentioned, that in the assigned statement we just tell or say what we are trying to do. Suppose we write A equal to B plus C, we are just saying that we want to add B and C and we want to store the result back in A, but you are not telling what kind of adder to use, how to add and so on. So, this is more like a behavioral description. Okay? We are specifying the behavior, but not the exact structure of the circuit. Okay. So, now we shall see a number of examples, typical usages, and while we are going through the examples, we shall also learn about a number of things there. Fine. This is one very simple example. We saw an examples of multiplexers earlier. So, here we are generating a mux. Like whenever we have a module description like this, now see, now right here we are not talking exactly about simulation. We are talking about what will happen when, let us say, we are using a synthesis tool to synthesize our circuit. So, for that purpose, what will happen? How the synthesis tool will be carrying out synthesis and what kind of hardware blocks or modules will be generated. So, let us see this example. So, in this example, you see that we are using a module called generate mux, which has 3 parameters. The input is a 16-bit quantity, it is a 16 to 1 mux, 4-bit select line and a single bit output. So, we are simply using a single line description which says assign out equal to data of select. So, data is like a vector, 16-bit vector, select is a number, 4-bit number which selects one of the bits and that particular bit goes to out. So, which is what mux is? Now, whenever the Verilog synthesizer encounters such a description, a multiplexer will be generated. So, how does the synthesizer know that a multiplexer will be required to be generated? The keyword is a non-constant index in the expression on the right hand side. So, whenever there is a vector which I am using with a non-constant index, select is a variable, right. it is not a constant. So, the index value is a variable, then we will be generating a multiplexer. Okay. So, the data whatever is there, that will be the input to the multiplexer, and this variable will go to the select line, and this out will be the output point. Now, the point to note is that, like as I had said with the example I have shown, that whenever there is an array reference with a variable index, the multiplexer will be generated. But however, if on the right side it is not a variable, it is a constant, let us say like this, assign out equal to data 2, then no multiplexer will be generated, because you see data is nothing but an vector. Okay? Vector means a collection of bits. So, it is a 16-bit vector. So, the indexes, the index values will go from 0 up to 15. So, when we say assign out equal to data 2, what will happen is that data 2 is this bit will straight away be taken out, and this will be called as out. So, no circuit will be generated, it will be just wiring. This particular bit will be connected, or it will be given a name out. Okay. This will be what will happen if I give an assignment like this. No gates or no hardware blocks will be generated for an assignment like this. But if I write like in the previous example, assign out equal to data, but I give a variable cell here, I do not know which bit I want. So, here you need to synthesize or generate a multiplexer, where the input will be your data, this will be your select lines, and on the output side you will be getting the output bit out, right. Okay. So, let us take another example. Here this is also an example for multiplexer, but we are using a conditional operator here. So, what we are doing, let us try to understand. This A and B are two 4-bit vectors. So, the index goes from 0 to 3 in this order we have said. Similarly, F is another 4-bit vector, which is the output, and cell is an input. And in this conditional operator, we are saying that if cell is true, cell is a 1-bit vector. If this is true, means it is 1, then you select A, else you select B. Select A means A will be assigned to F, otherwise B will be assigned to F. So, actually what will happen here? This will be generating a multiplexer, means every conditional operator will be generating a multiplexer, because it is if then else. But here this A and B are both 4-bit vectors, and F is also a 4-bit vector. You see, whenever you have a conditional thing, what you are doing? You are checking for a condition. If the condition is true, you are selecting one. If the condition is false, you are selecting the other. So, what you are actually generating is a 2 to 1 mux. You will be generating a 2 to 1 multiplexer. But here what has happened in the example that I have given, both A and B and F, they are all 4-bit quantities. So, actually it will not be one 2 to 1 multiplexer, but 4 such multiplexers will be generated. So, each of them will be having 2 inputs and 1 output. They will be having a common select line SEL, this will be connected in parallel to all of them. Now, in the inputs we will be connecting for the first one A0 and B0, the second one will be connecting A1 and B1, third one will be connecting A2 and B2, and fourth one we are connecting A3 and B3. And in the output side, this will go to F0, this will go to F1, this will go to F2, and this will go to F3. F3. So, you see a statement like that using conditional automatically generates an array of multiplexers like this, and these multiplexers will all be 2 to 1 multiplexers, right. Okay. So, here the point to observe is that, so whenever you have a conditional expression like the one we have seen, we have shown in the right hand side, automatically a 2 to 1 multiplexer will be generated. Now, in the example which I had shown, because A, B and F are vectors, so it was not 1, but an array of 4 such multiplexers were generated. Now, let us take an example. Suppose I have given an assignment statement like this. So, what will be the hardware this assignment statement will be generating? Let us try to work this out. So, our statement that we have seen is assign f equal to, this is a conditional. So, the condition checking that we are doing is a equal to 0. If it is true, c plus d, if it is false, c minus d. So, this is what we are actually trying to do. Now, let us see. So, here what will happen? Here there will be a multiplexer which will be, I am just showing one multiplexer, but actually it will be not one, but several multiplexers. I am using the array notation, 2 to 1 multiplexers using the array or the vector notation. So, it will be having 2 inputs, these are not single lines, but multiple lines. Similarly, it will be having an output, not one, multiple. So, in the select line, we will be comparing A with 0. So, there will be a magnitude comparator. So, I need a magnitude comparator circuit which will be taking A as input, it will be comparing it with the number 0, and the result of the comparison will be fed to the select line. So, either this will be true or this will be false. And on the other side, I use an adder where I have fed the numbers c and d, the sum I am connecting here, and I also have a subtractor where again I have fed the number c and d, this I am connecting here. So, this will be the kind of circuit that will be generated. Now, let us say if this adders, let us say this is all 16-bit operation, these numbers are all 16 bits, then actually this is a vector kind of a notation, the output is f. So, actually it will be not one multiplexer, but 16 such multiplexers will be generated, one for every bit of this data. There are 16 bits. So, 16 bits have to be multiplexed. So, I need 16 2 to 1 multiplexers, right. Okay. So, let us take another example. This is the example of a decoder, means this is an example which will be generating a decoder. So, here you see what we have given. Here we have one input, in is a single bit input, select is 2 bit vector and out is a 4 bit vector. And what we have written is something like this: out with an index a variable equal to in. So, now the array access with a variable index is appearing on the left hand side. So, whenever such a thing happens, a decoder will be synthesized. So, if we have on the left hand side a non-constant index select, then a decoder will be generated. So, what the decoder will do? The input value will be going to one of the outputs depending on select. So, now your circuit will be something like this. You have a decoder or a demultiplexer, whatever you call. The input will be in single bit data, but in the output there will be several lines. This will be your out, and this input will be connected to one of the outputs, and which one, that will be determined by the select line cell select. Okay. So, in an assignment statement, if there is on the left hand side an expression like this out with a variable in the index, then a decoder will be generated. Now, again if instead of a variable there is a constant, this will again generate a simple wire connection. This in, whatever is in, it will directly be connected to the 5th bit of the vector out. So, there will be no circuit that will be generated, just a wire. So, as I said, whenever the synthesis tool will find out a variable index in the left hand side, a decoder is generated, and if it finds a variable index in the right hand side, a multiplexer will be generated. So, these are some simple rules which the synthesis tool often uses or utilizes. Okay? Fine. Now, here we take an example where we are using an assign statement to describe a sequential logic element, which is actually a level sensitive D type latch. So, what does this do? Okay, this E will be in capital. Okay. So, what is this description doing? There are 3 parameters, D and enable are the inputs and Q is the output. So, what is this assignment statement doing? It is saying if enable is true, that means it is 1, then D will be going to Q. Otherwise, if enable is 0, Q will be going to Q. Q will be going to Q means it will be remembering its previous state, there will be no change. So, this Q will be going to Q, this kind of assignment whenever it is there. So, the synthesizer will immediately deduce that, well, I need to generate a latch or a memory element, because I have to memorize some data value. So, as this example says that for certain condition of the enable, when enable is 0, I have to remember the value of Q, because the output Q will be equal to the old value of Q. Okay. So, this will correspond to the state table like this. So, when enable is 0, this Q will be selected. So, D will be do not care, irrespective of D, whatever was the previous value of Q, I am denoting as Q n minus 1, that will be the new value of Q, I am calling it Q n. But if enable is 1, then whatever is the value of D, that will be copied to Q. Okay. So, this single assign statement will be generating a D type latch. Similarly, if you look at a simple RS or SR type latch using a cross coupled gates, here I am showing NAND gates, cross coupled NAND gates. So, a circuit like this which has 2 inputs R and S and Q and Q bar. So, if you again look at the state table, what will happen? If both S and R are 1 and 1, then whatever is Q bar, Q and Q bar, let us say Q is 1 and Q bar is 0, if this is 1, 1 will come, 1 and 1 will be 0 and 0 and 1 will be 1. So, no change. Similarly, for the reverse. So, when the inputs are 1 and 1, the previous input value will remain. This is the behavior of this circuit. Okay. But if S equal to 0 and R equal to 1, S equal to 0 will force this output to become 1. So, Q bar will be 1 and Q will be 0, because if Q bar is 1, this 1 and R equal to 1 will make the output of NAND gate 0. So, Q will be 0. Similarly, if S is 1 and R is 0, the reverse will happen. If R is 0, Q will be 1 and this 1 and 1 will make this 0, and hence this is 1. But 0 0 is an indeterminate state. If we apply 0 and 0, then you see these are NAND gates, both input outputs will become 1 and 1, which is inconsistent with Q and Q bar. Not only that, after that if I apply 1 1, what is Q n minus 1, that will be confusing to the hardware and also to the simulator, okay, because this is not a valid state, both Q and Q bar is 1. So, which one will become 0, that will depend on the relative delays of these 2 gates, which one is faster, that will force the output to it to change first. Okay. That is called race condition. Fine. So, this circuit, exactly the way I have shown here, you can use 2 assign statement. In one assign statement, you are using the NAND of Q bar and R to generate Q, and the other one q and s to generate q bar. So, just like this two assigned statements. This is NAND and then not, R and q bar, this is q, and s and q, this is q bar. Just two assigned statement will be generating two NAND functions, and this will be specifying the behavior of this latch. Now, just for the purpose of testing, we also wrote a sample test bench for this, to check whether this latch is actually working like a latch should work. We wrote a test bench like this, where this SR latch was instantiated, we call it LAT. So, this S and R, which are the inputs, were declared as reg, and Q and Q bar, the outputs, were declared as wire, and we monitored all the variables S R, Q and Q bar. So, what we did initially, we set the input SRR to 0 and 1. So, if the inputs are 0 and 1, the output should be 0. Okay. Then we set the inputs to 1 and 1, so that the output should not change. Then we change to the other state 1 and 0. So, the output should become Q should become 1, then 1 and 1. Then just for testing, we applied the invalid condition 0 0 followed by 1 1 to see that what the simulator does here. So, what the simulator did was something like this. First few lines was absolutely perfect, what we expected. S 0 R 1 generates Q 0 and Q bar 1. Then we apply both 1 1. So, the same state remains, no change. Then we apply 1 and 0. So, Q becomes 1 and Q bar becomes 0. Then 1 1, same state, no change. Then we apply S equal to 0, R equal to 0, which is 1 and 1, but after that we again applied 1 1. But the problem is that the simulator got confused and the simulator hangs. It continuously tries to deduce that what will happen when S equal to 1, R equal to 1, but because of the race condition, the output never converges. So, simulator assumes that the two gates have exactly equal delays. So, when the outputs are 1 and 1 and you apply 1 1, outputs will become 0 and 0, next state it will again become 1 on 1, next state it will again become 0 and 0. So, both the outputs will oscillate indefinitely, it will never converge, and the simulator will go on trying to compute the output value indefinitely. So, this was exactly what was happening here, right. So, the crux is that you should not apply such invalid inputs to an SR flip flop in actual circuit operation. So, with this we come to the end of this lecture, where we have actually looked at some of the modeling styles. In particular, we looked at the assign again. We took some examples of assign earlier also, just work out a number of examples. We again saw assign here, and we saw that not only combination circuits, we can also model sequential circuit elements. Whatever circuits I can draw using gates, I can also implement that using assigned statements. Like you know how to design flip flops. I just showed the example of a cross coupled NAND gates. You can design a JK flip flop, SR flip flop, T flip flop, all using gates, NAND gates, NOR gates, then H triggered flip flop. So, once you have a gate level circuit diagram, using assigned statement or using instantiation of the gates, you can create those designs. So, those are also some ways to create sequential circuit elements in Verilog. So, in the next lecture, we shall be continuing with some more Verilog constructs and examples. Thank you.